Thus far in this series of lessons on oscilloscope measurements, we have only talked about time domain measurements, which means displaying waveforms in an amplitude versus time format, where amplitude can be voltage, current, or power. But as you may have learned in your circuits classes, all time domain signals can be decomposed into multiple sine waves of different frequencies. When these sine waves are summed together, they produce the time domain waveform. Hi, I'm Johnny Hancock, Product Manager for Keysight Technologies Infinivision Oscilloscopes. As you can see in this three-dimensional graph on your screen now, there are different ways of looking at a signal. The graph on the right shows a frequency domain representation of a signal that consists of two sine waves at different frequencies and different amplitudes. Amplitude is on the vertical axis, frequency is on the horizontal axis. The graph in the middle shows the two individual sine waves in a time domain format. The graph on the left shows the summation of these two sine waves to produce the final time domain waveform, which is what we would typically view on an oscilloscope. Since I'm primarily a digital engineer, operating and thinking in the time domain is more intuitive to me. But for many electrical engineers, especially those that work in the RF communication world, the frequency domain is more intuitive. There's an instrument that many RF designers use a lot called a spectrum analyzer, where the primary measurement domain is the frequency domain. Your university probably has some spec-ans in some of the research labs. Although the oscilloscope's primary measurement domain is to display waveforms in the time domain format, all of today's oscilloscopes have a math function called FFT, which stands for Fast Fourier Transform. An FFT operation converts a time domain waveform into a frequency domain trace to emulate what a spectrum analyzer displays. Let's now convert a repetitive clock signal or square wave from the time domain to the frequency domain using the FFT math function. So here's our VN on our resistance divider network, our 10 volt peak to peak. I'm going to change this to a square wave, or you might call it a clock signal. And we're going to do an FFT, Fast Fourier Transform, on this, but my first recommendation is to get more cycles on screen. You can get better resolution for the FFT if you have more cycles. Then you can either go into the math menu and select FFT, or we have a dedicated knob on this, or not knob, but button on this scope that says FFT. We just pulled it out since it's such a popular math function in the education environment. So I'll select FFT. Now, this is the FFT. Each of these purple peaks here represents a sine wave of a different frequency. The one over here on the left is the fundamental, which is 20 kilohertz. The next one to the right should be the third harmonic, next one, fifth harmonic, and so on. Now, you can rescale your FFT very similar to the way you rescale vertical and horizontal on the time domain waveform. So right now, this is our time domain input signal. It's scaled based on seconds per division. The frequency domain FFT trace or waveform, it's scaled based on span, the total frequency from the left side to the right side. Right now it says 1 megahertz. If you wanted it in frequency per division, just divide that by 10. So we're basically 100 kilohertz per division. And then we have the center set at 500 megahertz. Now we can make measurements on this signal as well. Let's rescale this down a little bit so we can see it more clearly. We could turn on the cursors, select FFT, and then I could select the Y1 cursor and position it at the top of the fundamental, and it's measuring 13.13 dB volts. Now, you may not understand what dB volts is. I'll show you in a minute how we can change it to volts. And then let's measure the frequency of that one. Let's change it to X2 cursor and adjust that until it's right on top of the fundamental peak, and it measures 20 kilohertz, just what we expect. Well, let's slide down and measure the next one. That one measures, it says 61 kilohertz, but I bet it's 60. I didn't place it very accurately. The next one, 100 kilohertz, and so on. And so this square wave is made up of an infinite number of odd harmonics. Now, I mentioned we can convert it back to volts. This is a logarithmic display. That's why it's in dB volts. We can go into the settings menu and say, I want to see it in terms of volts RMS. Let's rescale this. And now if we put the cursors on it, we would measure an absolute voltage. But in absolute voltage, you can see the higher harmonics visually are very suppressed. The advantage of the logarithmic scaling, which is pretty typical for frequency domain measurements, is that it visually expands the harmonics that have lower amplitudes. So let's go back to dB volts. Let me get this repositioned again. And what about other wave shapes? So this is what a square wave looks like, the fundamental and all the odd harmonics. What if we selected a triangular wave? Now you get odd and even harmonics. What if we selected a sine wave? Theoretically, we should get one peak only, and that's the frequency, that's that peak there at 20 kilohertz. So here's an interesting application. I'm using one of the built-in education training signals of this scope. We use this to train students on FFT. This is a 1 kilohertz square wave or clock signal, and it looks like it has lots of noise riding on the top and bottom of the waveform. But is it really noise? Well, let's find out using FFT. So I'm going to turn on FFT, and I've already got the span and the center set up to demonstrate this. This is the fundamental way at the left. If I put cursors up, I could measure it. I would see it, it's at 1 kilohertz, and then all the other peaks are 3 kilohertz, 5 kilohertz, 7 kilohertz, all of the odd harmonics of the fundamental. You add all those up, and it has sine waves, and it creates the 1 kilohertz square wave. But there's an oddball, this one out here. It's sticking way up. It's not continually to decrease in amplitude. That is a component of coupling. Now let's measure it. I'll turn the cursors on, and let's just measure the frequency. I'll put it out here, and it measures about 89 kilohertz. There's an 89 kilohertz sine wave coupling on to this 1 kilohertz square wave, and FFT popped it out right away. In our next lesson, we'll be talking about Bode plots, which is another type of frequency domain measurement, where gain, which is V out divided by V in, as well as phase, is plotted versus frequency. Remember, for additional technical resources to help you learn more about oscilloscopes, go to the URL listed on your screen. See you in Lesson 10. Go Oxford!